So this video is going to show how to do some of the basic descriptive statistics exercises in R. So in particular, I'm going to do problem 6 out of chapter 3 of Siegel, which then becomes problem 29 in chapter 4, and then problem 36 in chapter 5. So we'll do 3.6, 4.29, 5.36. All right. This problem uses data that I've now typed in, and it's available from Canvas in a file called tab 3.9.1. So you need to download that file and put it somewhere on your computer where you know where it is. All right, so I have stuck this file in a folder called Teach, then 451, then Siegel data, and the file name. Again, I don't care where you put it, but just put it somewhere where you can find it. So let's bring it in. I'm going to bring it in. I'm just going to call it an object, call it dat. I like dat, it's fine. And so we'll do a read CSV to bring this in. So remember I said on my computer it was in Teach, then 451, then Siegel data, and then I think it was tab 3.9.1. .csv, and if I hit enter, R is happy because it comes right back. So let's go read through the data set. What we have are some yields of municipal bonds. So this is what it should look like when you type DAT. So you have various bond names and then their yield over some period of time. Part A, so this is question 6 in chapter 3, says construct a histogram. So let's go do that. Now remember, if you type names on an object, you get all the names of the variables. So names $yield gives me these yields. So if I then type hist name dat $yield, I'll get a histogram of that. And so here is that histogram. Part B says, based on the histogram, what values appear to be typical? Well, what it really looks like is you have kind of a normal distribution with some outliers out here. What is typical? Well, here's kind of the center of the main distribution of data, meaning everything but the outliers. So I'd say a typical value is about a 5.2% return, 0.052-ish. Somewhere in that area would be typical. Describe the shape, we just did that. So it's normal, we got a couple outliers. And it looks like that's it for the problem in chapter 6. So let's now move on to problem 29 in chapter 4. So 29 says go back to table 3.9.1. We already got that in. And part A says find the average, B is the median, C is the quartile, D is the 5-number summary. So if we're clever about this, we can knock off the first 4 or 5 parts with a single command. So if we do a summary on this, we have the answer to part A. So the mean is 5.218%. Here is the answer to part B. Quartiles are those two numbers, and then the 5-number summary is everything but the mean. Not that you need to know this, but there is actually a 5num command that gives you the 5-number summary, but might as well just use summary. Part E then reads, construct a box plot. So if I do box plot this, we get a box plot which confirms our conclusions from the histogram. So this box is looking pretty normal, and we've got a couple outliers. Part F says identify the outliers, if any, and draw a detailed box plot. All right, so one way we could identify these outliers is notice that these outliers are above about 0.056%. So you could let's build up a command. If you say dat $yield greater than 0.056, you're going to get a bunch of trues and falses. So most of these observations are false, and then there are 2 trues. So it looks like it's this happens to be the 12th observation. Notice the next row is, this is the 13th, and then it looks like the 22nd or something. So if we just wanted to display those 2 observations, what I could do is this. I could just say dat of this, comma, close bracket. Now, what is this going to do? Well, the first part displays the rows, all right? So everything before the comma is just saying which rows do you want to show. So we want to show only the rows where the variable yield is greater than 0.056. Now, the second thing after the comma would be the columns, and if I just leave it blank, that means give me them all. All right, so notice we have observations 12 and 21 are the outliers, so whatever those funds are. All right, find the, I told you to omit G. As for H, I don't think it's terribly important. If you really want to know the answer, you can do ECDF dat $yield, and then you have a second set of parentheses, 0.054, and it tells you, this is for the empirical cumulative distribution function. It tells you that 5.4% is about the 90th percentile, so that 0.9 means 90th percentile. Finally, part I says find the value of the 60th percentile. This one's easy. We're just going to use the quantile function, dat $yield, and we're asked for the 60th percentile, so if you say 0.6, you get the 60th percentile, so 5.23%. And that's it for problem 29. Let's now move on to question 36 in chapter 5. So let me go find that. 36 says, what is the standard deviation of yield? Well, the easiest way to find the standard deviation of yield, I'm kind of a lazy typist, so I like to bring up previous commands. Find standard deviations with the SD command. So there is your standard deviation. Part B is what is the range? So, if we go type range, not rage, you get the actually the minimum and the maximum value. That's not what Siegel means by range. He means the difference between those. So if you're very lazy like I am, you can just use diff. And so if you add a diff around all that, it computes the difference. Or you could just type the numbers in directly. So 0.0583, I'm taking that from this output up here, minus 0.0491, and so you get the same answer, but diff is kind of, I don't know, I find it a little bit easier. Part C, what's the coefficient of variation? So remember the coefficient of variation is the standard deviation divided by the mean. So we could do dat $yield, and that would be our coefficient of variation. It's often expressed as a percent, so if you really want to make it a percent, multiply by 100. I'm using the up arrow to bring back the previous command. Use these summaries to describe the extent of variability among these yields. Well, there's not a lot of variability. So about 1.7, or about 0.2%, if we round that to 0.002, is the typical deviation from the mean. So 0.0017 is the typical deviation of an observation from the mean, which means they're fairly tightly packed, dispersed. And that's